All right, thanks. It's always hard to follow you, James. And James and I actually have been working a lot on energy efficiency, power conversion, and so on. That's one of the big sins, I think, that our industry is still committing routinely today. And in my talk, I'm going to talk about another sin that I think we all are routinely committing, namely to not take speed seriously enough, both from a business perspective and from a product perspective. So speed matters, and I am going to talk about speed matters in this talk. First, how fast can the web really be? We had some fun earlier today. Please roll the video. And you can see that the web can be faster than a speeding potato. All right, so the web can be faster than a speeding potato. But, you and I know that in our average web experience, that's not actually the case. Here are some numbers that we collected from millions of browsers, right, anonymously. The average page load is 4.9 seconds, right, across many, many users, many, many websites. The web pages are pretty big, 320 kilobytes. And the average bandwidth that users have worldwide, right, that's average, is 1.8 megabit. Now, if you look at these numbers and you just kind of divide them out, 1.8 megabit is a little bit more than 200 kilobytes. 200 kilobytes per second. So 320 kilobytes should only take about 1.4 seconds. And so why does it then take almost 5 seconds to download the average web page? It's not the network, really. Here's a waterfall chart of a typical page load, in this case, CNN.com. And what you can see is that there's lots and lots going on. Right? You have some DNS lookup in the beginning and actually repeated. You have connection setups. You have actual server response time. You have data transfers. And then you have a lot of just parsing and executing the HTML and the JavaScript on that page. So the average web page isn't just big. It's also relatively complicated. So we saw the size before. Typically, or on average, has 44 different resources or elements, JPEGs, JavaScript, et cetera, on it. Makes 7 DNS lookups, and doesn't compress a third of its content, which would be compressible. Okay, so web pages aren't really just an HTML, right? It's really a big ensemble of lots of things, some of which need to go serially even. And so our goal is to, in fact, make the web as fast as a speeding potato, right? Or actually, a better analogy might be as fast as reading a book, right? We want web pages to be, for you to be able to flip from one page to another as quickly as you can flip a page on a book. So we're really aiming very, very high here, something like 100 milliseconds. And for that to be true, right, from 5 seconds, we obviously need to make really radical improvements. And what I'm talking about in the rest of the talk is that, in fact, many of these improvements are already in the works. And if we all as an industry work hard together, we can easily get a factor of 10 and possibly more. So first thing to do, obviously, is to make the browser itself faster. So we spent a lot of work on Chrome, our browser, to make faster and faster web page downloads, JavaScript execution, and so on and so on. And now we rank, reliably at the top of pretty much all benchmarks. Here's one from Beta News that measures, JavaScript and a bunch of page downloading, et cetera. You see Chrome 4 leading. Chrome 5 just came out. It's even faster than that. Chrome has a lot of things in there that anyone can do, meaning any browser vendor can do. HTML5 makes a lot of things faster. better JavaScript engine, right? Much, much faster than previous JavaScript engines. Again, actually not reinventing really anything new, but using techniques that were invented in the 90s, applying them to JavaScript and speeding up things by literally factors of between 2 and 10 relative to previous interpreters. We make lots of other innovations. Some of them mentioned here. DNS prefetching, for example. The browser goes and already does DNS lookups if it sees elements on the page even before these elements actually are needed. We have an open-sourced video decoder of a state-of-the-art video. In fact, all of this is open source, and our goal isn't to take 100% of market share of all browsers. Our goal is to move the industry forward by showing what's possible, by making it open source, and by pushing others to adopt these improvements. And the push is really indirect because, hey, look here, it's open source. It's clearly good for the user, so please adopt it. And by the way, if you don't, here's a better browser that beats yours currently. So you have a choice between either competing or between losing users. Right? And we think that's good for the industry to move that forward. And in fact, that competition, spurring competition is working. Here's a graph of the average page load time divided up by browsers for the other two major browsers on the market. And you can see they really have improved significantly over their previous instances. Right? So they actually are doing a good job at working on speed already. Now, beyond that, we need to do a lot more. One of the things is improve protocols, the protocols that underlie the internet. Many of them were devised a long, long time ago. So TCP was devised in 1980, in the 80s, right, early 80s. And it's actually amazing how well it has held up, right? The people did really a superb job in designing it. At the same time, the assumptions that stand behind the protocol were really radically different, right? Back then, a 56 kilobit line was considered high speed, right? And you literally had networks whose cross-country backbone was 1 or 2 65 kilobit lines, right? And so many of the parameters and many of the assumptions underlying TCP are from a world where networks were 10,000 times slower than today. And so even though the protocols still work, they don't work optimally. And one of the things that we've been working on ourselves is very modest revisions to TCP, mostly to parameters in TCP, to tune it for modern networks. We published a paper on this and submitted an IETF draft that shows that with some simple ways, you can get a 12% improvement on speed, even for an optimized site like Google, without changing the application or the web pages at all, right? So this is purely the TCP implementation, and the changes in there are literally, tens of lines of code, not very major. So hopefully that's going to be widely adopted. Here's just some example. Look at the blue bars. This is the percentage of improvements across a number of Google products, and you see that, for example, for Google Images, you get an 18% improvement, and this is measured on real traffic for image.google.com, right? Just by tuning TCP. DNS itself, right? So the resolution of a host name to an IP address can also be improved mostly for global load balancing. So today the problem is that if we as Google want to direct you to your closest web server, we actually can't really tell where you are, because when a DNS request comes in, it doesn't come from your desktop, it comes from your ISP's DNS server. And ISPs may actually aggregate the DNS servers, for all of California or the Western US in one place. And so we don't see the difference between someone being in Washington State and someone being in Southern California, right? With a DNS improvement that we proposed, you get enough of a fragment of the client address together with the DNS request so that you can actually see, okay, the client is in Southern California versus in Seattle, and then choose a different data centers to direct them to, and typically closer data center is faster. SSL, another fundamental protocol, has some fairly basic problems, not functionality problems or security problems, but speed problems. Right? So it needs, pure SSL needs 2 handshakes, so 2 round trips to a server. So that's typically a quarter of a second right there, just to start sending useful data. And then on top of that, in a number of instances, it needs to go check a certificate. And if you happen to be in Asia or in another part of the world where the certificate servers aren't close, that can easily add another second to your connection time. And so it's a really high penalty for SSL. We proposed approaches for all of these problems to get the average penalty for an SSL round trip to be close to 0 because all of these things happen again and again, and you can cache the right information in a secure way and avoid these overheads. So on Android, for example, we've implemented, in fact, the SSL improvement. So if you use Android SSL, it's about 10% faster than it was before because it already, when going to Google, uses the improved protocols that eliminate this overhead. And finally, HTTP, right, the protocol that actually delivers the web pages, actually has some of the largest potential for improvement. The big problems, the 2 big problems there are that, as we see, the average page has 44 elements on it. And these elements are all loaded through separate requests. And that ends up wasting a lot of network bandwidth because really you're kind of waiting for responses rather than streaming bytes from the server to the client. And so you never actually reach the network speed that your network line can provide because you're always waiting for a round trip to complete. And there's a lot we can do there. We implemented a few things. This, again, is an IETF. Actually, I think it's an IETF draft. But certainly open source published, implemented in Chrome, and implemented Google server-side. We're actually experimenting with this and seeing some very, very encouraging results, even in early, given that's a 1.0 thing. So see a 25% improvement in page download time. Again, without changing the website or the application. Right? It's purely a protocol improvement. So this would be like an Apache module for most websites, and then a browser side implementation. Here's some details. And at the end of the page, at the end of the talk, I'm going to have lots of links with many of the details. So here's SPDY downloading the top 25, so the top 25 most popular websites in the world. And you can see that just through the protocol improvements for all of these downloads, 25 downloads, in total, 40% fewer packets are sent between server and clients. And the number of bytes transmitted also goes down. And the number of packets actually is very important because every packet incurs a round trip. It needs to go from you to the server and then come back. And that is, many of these round trips are what's actually inhibiting full network performance. And so with 40% fewer packets, you can get speedups of, as I mentioned, 25% area. Another, in retrospect, sort of obvious technique that is in SPDY is header compression. Right? When your client talks to the same server over and over again in order to fetch all the elements of the page, it sends the same headers in both ways all the time. Right? Your browser says, oh, I'm Mozilla 3.6, blah, 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 I accept gzip, and UTF-8, and blah, 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 right? And you do that 44 times, right? There's no actual information exchange there after the first time, right? It's just repetition. And so in a protocol, you can easily squeeze that out with compression. You can see here for CNET, right, another popular site, you get an 88% reduction in header bytes that are being sent between client and server. And if your line is a little bit slower, so if you're maybe on a wireless with a little bit of problems or whatever, just these headers can cost you a second in your overall page download time, right? And remember, these headers actually didn't provide any useful value or 80%, 88% of it didn't really provide useful value, right? So we need to get rid of that inefficiency, just like we need to get rid of inefficiency in energy usage. And then finally, there's also some infrastructure things that we can do to make the web faster. That means for you, right, it means provisioning your servers such that you are not totally overloading, realizing that time is money. Right? I haven't talked about this because at the last conference, there were several papers showing that actually revenue correlates to speed. In fact, just this week, About.com published a study where we've been working with them to speed up their website. They got a speed up of about 20%. And they showed very measurable revenue improvements, right? Millions of dollars per year for them in additional revenue because they get more page views and they get more clicks. So for you, infrastructure means make sure you understand the economic impact of time and provision things, right? What we decided to do is two things. One is because we saw that DNS performance was often a contributor to slowness, and really for no good reason other than for suboptimal provisioning of the DNS infrastructure. So we're providing the Google public DNS. If you want to set your system to use it, just have it use 8.8.8.8 as a DNS server. It's a very well provisioned, globally distributed DNS, recursive DNS server, highly available, and also very fast. Right? Among the things that it does is it proactively refreshes the cache. Right? So typically in DNS, right, your entry has a certain cache lifetime, and the DNS resolver ages it out when when that time is over, and then it waits for the next request to come in for that name until it goes and refreshes it. Right? That's really unnecessary delay. That's an unnecessary delay for these kind of hosts. And keeping actually sort of pretty much all the world's DNS refreshed isn't actually that hard, because in a grand scheme of things, there's only tens or hundreds of millions of DNS names, and they fit comfortably into the memory of a server today. Right? So this isn't really a cost thing, right? A megabyte of memory costs basically nothing these days, especially if you can use it to provide a service to millions of people. Another infrastructure project that we've announced, but we're not actually doing yet, is just to see what happens if your network speed was definitely not the limit anymore. So that's to provision to the home network links that are 100 times faster than what you typically get today, namely full gigabit to the last mile in a one or a very small number of communities. And then use that also as a test lab for how do people behave if their network is really, really fast. Right? Now, one of the things I can tell you is that for most websites, the way they are written today, right, and because they're using protocols that weren't tuned for a fast web, they're not going to reach anywhere close to a gigabit, right? Not even remotely close, right? Because the protocols, the software, ruins the network performance, really. Right? And so all the things that I talked about so far really need to be fixed for users to have a faster experience as their network speed increases. And it's very clear that the network speed itself will increase. Right? So of all the things I talked about so far, with protocols, right, with faster browsers, I think we can easily get a factor of 2 in performance. Right? Most likely, actually, a factor of 3, sort of for the average web server worldwide. And it's very easy to conceive that we can get another factor of 3 from networking improvements. Right? So the average speed worldwide goes from 1.8 megabit to 5.4 megabit. That's very, very conceivable. Right? This will happen. Right? However, if we don't fix the protocols, we will not actually be able to exploit that extra bandwidth, because your TCP connection, your server connection, is never in a mode where the server actually just streams back at your line rate packets to you, right? in the current protocols, everything is waiting. Like I send a little bit to the server. I need to wait for the server to respond. The server, before it sends the next thing, has to wait for me to respond, et cetera, right? That ruins network performance. And in a testbed like this one, this will be very apparent. And then finally, we also, as a community service, host some popular things that make it possible for websites to use commonly used resources like jQuery and not by themselves get slowed down because the jQuery file serving is slow. And similarly also, web fonts, a number of other things that web pages do. We also pay a lot of attention to make sure that our AdWords and AdSense tags or the Google Analytics ones don't slow down web page load. So if you are using AdSense or Google Analytics, make sure you actually have the newest code snippet of those versions because they are tuned really to not delay your page download for the analytics or for the ads, right? Because everything happens asynchronously and is really tuned for good performance. Finally, for all of you who are developers, we are working hard to develop tools and to provide them for free that make it possible for you to actually recognize what's wrong with your site and to go fix it. Chrome has a lot of these things built in. Our open source sites provide all of them. I'm mentioning just a few here. So measuring the speed of your web page and which elements contribute, how much is one, or Closure. The Closure compiler helps you make more efficient and more compact JavaScript. The Autosprider, for example, can combine multiple images into one, reducing the number of round trips that go to the server, et cetera, et cetera. One reason I'm here is really and actually one reason you are all here and one reason this conference exists, is to create more awareness about how important really is speed is, right? Larry Page of Google, right, he's often said, as a product manager, you should know that speed is product feature number one, right? And then your next one is, whatever it is, right? But think about it, the most successful applications, right, both on the internet and off, right, they're games, right? Game developers, they understand that speed is essential, right? And for them, speed is feature number one, right? If you have a car driving game and it's sluggish, you're not going to play it, right? We need to understand that too, that not just for gaming is speed important, but actually for almost every application, right? It makes your product more liked, right? It makes it easier to use, right? It makes it less scary to click a button if you know that the page is going to refresh right away, and then you can see what happened with it, et cetera, et cetera. Right? We see that again and again. Right? So here's some ways how we do create awareness. And actually, in the Google search ranking, we are now taking speed as one of the factors in ranking into account. So if your website is slow, then you're going to drop down on the rankings because we have seen that users do not like slow sites. So if there are two equivalently ranked sites, then we are providing a better service to the user by putting the faster site up front. Right? It's documented on our website. We have actually a whole section of our code, .google.com repository, dedicated to speed. BrowserScope website that really helps you understand and measure browser data. A lot of the numbers I mentioned is in a site performance data site, so you can go look up detailed statistics about average page size of large sites, of small sites, et cetera, et cetera. We want to make that all available so that you can actually better gauge how your users look like in terms of their connection speed and how your website should behave. And so that's really my last point here. This isn't something that Google can do by itself. We do it for our site, right? And so that obviously benefits a lot of users. But for the internet to stop being wasteful about speed, we all need to do our part, right? So if you have your own website, that means you need to go and understand, that A, users like speed, both explicitly and implicitly. B, users react to speed, and they will spend more time and more money on your site if it is fast. And then C, there are a lot of relatively simple things that you can do with all these tools that are out there that help you speed up your website. And then beyond that, we really need to renovate some of the infrastructure in the web. The protocols that I mentioned, improvements to HTTP, SSL, TCP, that all cost today some overhead that is really avoidable. And then finally, we just need to remember that nothing is for free, right? And the reason why today many things are slow is because just of a lack of focus. It's really the same reason as in data centers why many data centers are inefficient. It's a lack of focus, and it's a lack of someone looking at the total cost of the whole operation. Right? And if you look at the total cost of the operation of a website, you got to look not just at the cost of providing it, but also at the revenue that it does generate. Right? And so if you put in more effort, people time, into making the website faster, this may very well be a negative cost, right? So far, certainly for us, this has always been turned out to be a negative cost, meaning that we win, right? We spend money and we get a high return on the investment by doing that. So I really encourage you to look into these things. I have lists, some links mentioned here, and I think the slides will be online, and this is all also easily findable with your favorite search engine. And so please, spend time looking at that, and also convince your colleagues that it is very, very important to take speed as feature number one of your website. So with that, thanks very much for listening, and I hope you have a great conference.